My name is Pedro. I work for Cisco in Switzerland. And today I'm going to show how to make your data structures.
And then the Slack you can just put in your pocket.
Yeah. I hope that's better. Yeah, that's better. Even I can hear now. I'm going to show you how you can make your data structures wait-free for reads. But before we do that, we need to understand what is wait-free, what it's used for, what are its properties, how it compares to lock-free and blocking. And so we'll take a little bit of time to go over that before we go into the really good stuff. So this is like the outline of what I want to go through today. Talk a little bit about reader-writer locks, copy on write, and then the left-right pattern and how to use it. So progress conditions. Progress conditions come in many flavors. This is a really nice schematic from Maurice Herlihy and Nir Shavit. If you don't know who these guys are, those are the ones that wrote The Art of Multiprocessor Programming. And they have this white paper, I guess, on the nature of progress, where they talk about this stuff. And today I'm going to talk a bit about some of the things, like starvation-free, lock-free, and the different types of wait-free. I'm not going to talk about the other ones. They're not relevant for what's coming next. But you can go and read their paper if you want to learn more about this. So if you kind of represent the non-blocking conditions in progress conditions on a Venn diagram, you get something more or less like this. And the interesting part about this is that whatever wait-free, whatever lock-free provides, or whatever kind of guarantees lock-free provides, wait-free will also provide those guarantees and more. And whatever wait-free unbounded, in this case, provides, wait-free bounded will also provide and more. So that's the idea we're trying to pass here. And these are the definitions, but we'll go over each of them. Now, the first thing that most people get confused a little bit about is that progress conditions are not about time. They're about the number of steps it takes to complete some kind of tests and kind of work. And this is particularly confusing for wait-free because the word wait means some implication with time. It's like you're waiting for something, or so if it's wait-free, you're not waiting, so there's like no time or something. But that's not directly what the definitions talk about. The definitions talk about the number of steps needed to complete some task. So we have to be careful about that. Another thing is that when we think about these progress conditions lock-free, we think, oh, if it's lock-free, then it's very scalable. That might be so, but not necessarily. What it does have a lot of strong implications is on latency, how lock-free and wait-free work. And we'll see a little bit, just a tiny piece about that. But this has very strong implications about latency. So if you care about latency, you have to care about this. So the most simple that everybody knows is blocking. When something is blocking, you have to wait, and you may wait indefinitely. Now, just because it's blocking doesn't mean it won't scale. In this particular example, we're doing some computation that can be done like parallelly with some data that belongs just to this thread. And when we finish this computation, we put the result in some, in this case, we just add, so whatever. But we keep that result that's going to be shared. Now, you can think, how many threads would I be able to add to this and still scale something, and up to which point I would be able to scale? Now, if you think blocking, oh, it's blocking, so it won't scale anything. Well, that's not true. It really depends on a thing called Amdahl's law. And in this particular case, I don't know if anybody wants to take a guess how much this would scale. You have 5 times more the parallel side as you get on the serial side, which is the lock. So it should be able to scale up to 5 threads, let's say, something like this. I'm not going to go into Amdahl's law, but it's just to show that just because it's blocking, doesn't mean it won't scale. It will scale up to a certain point, and then it will reach a plateau, or maybe even start to go down. So quiz 1. Suppose you have two methods, they're very similar, and the only difference is that the part that's non-serialized, the part that's non-protected by the mutex, which is completely independent, takes slightly different times in proportion to the time it takes to save that data. So which one of these two methods is going to scale better, or let's say, is going to scale up to more threads? So that means you can add more threads and get more work done. B? Everybody's for B, I guess. Okay. So the answer is yes, it's B. You add more threads. You can add more threads and still get more work done. Now, funny enough, for A and B, you get the same kind of work done, which is because they have the same bottleneck in this case, which is the mutex. But yes, the answer is that. So just keep that in your mind when you think about blocking and scalability at the same time, what that implies. Sorry. Now, inside blocking, there are several properties. The one that I'm more interested about is starvation-free. Starvation-free has strong implications on latency. And the thing about starvation-free is it gives the guarantee that progress is going to be made as long as the other threads are making some kind of progress as well. So if the other guys are making progress, the other threads are making progress, eventually your thread is going to make progress as well. This is an example of something that is not starvation-free. It's just a spin lock. I think Fedor showed a spin lock using exchange. This one uses compare and exchange. But it's something very simple. And the thing is, you have this variable that's being changed from 0 to 1 as the lock is acquired or released. And you can have a thread that's waiting indefinitely for the lock, because whenever it tries to see, oh, it's already unlocked, let me do the cast, but then some other thread comes in and does it before. And then, oh, okay, now I'm going to yield and wait a little bit and then try again. And by the time it tries again, some other thread jumps in front. And this keeps happening theoretically forever. So this one is not starvation-free. This is actually very prone to starvation. An example of a lock that may or may not is here. This is actually called the ticket lock, so for those who know locks, the answer to this one will be very easy. So basically we have two variables, two atomics, and the first thing we do is do fetch and add on the variable ticket. This will give you a ticket. That's a numerical value that you keep. And the lock will be yours once the grant becomes equal to the ticket. So it's two counters that are monotonically increasing. Basically, that's what's going on. And then, if it's not your time to take the lock, then you wait, you yield for a little bit until it is. Anybody wants to guess whether it's blocking, starvation-free, or non-blocking? Blocking? Starvation-free? I don't hear more, okay. Nobody wants to take a risk, okay, that's fine. So the thing is, it is starvation-free, at least on x86, because the fetch and add operation is a single atomic instruction. So there are no retries, you do it just once. And because you do it once, now you have a ticket. And that ticket is the numerical value of when is your time, when is the time for this current thread to go in the lock. And that means that no other thread can pass in front of you. Eventually, it will get to your ticket, and all the other threads will be yielding, waiting for you to take the turn, and then waiting for that thread to take the turn, and then it's it. So there's always a finite number of steps, which in this case, it's called the linear wait starvation-free, because each thread has to wait at most for n threads, or n-1 threads. And there are many examples of starvation-free locks, besides the ticket lock, CLH, TDEX, which we discovered. And now you have lock-free. Now, the definition of lock-free is it written there? So I'm going to read it because I don't know it by heart. A method is lock-free if it guarantees that infinitely often some thread calling this method finishes in a finite number of steps. Now, an easier way to prove that something is lock-free, or to understand, which is a subset of what's written there, is to just say that if you have a thread calling method, and you can guarantee that at least one is going to complete in a finite number of steps, then it's lock-free. It may not seem like much, but it is a really strong condition and very hard to guarantee in practice. Now, the thing about lock-free that maybe most people don't realize is that lock-free implies the possibility of starvation. If you have a method that's lock-free, it can be starved. Now, in practice, if it's a good algorithm, lock-free algorithm, this will only happen for very high contention, very high number of threads and cores. But it can happen. So again, keep that in mind, especially when compared with starvation-free. So it's like, yes, starvation-free is blocking, but it won't starve. Lock-free is non-blocking, but it can starve. So you need to keep that in mind. It has strong implications. And this little bit of code is just the insertion in a queue or list using Meg Michael and Michael Scott's algorithm. For a lock-free. So basically you just have a linked list and you're trying to put in the end a new node, and if it fails, you do that with a compare and swap, and if it fails, you try again and you try again and you try again, and theoretically it can go on forever, but it's lock-free because the only reason why it might fail is because some other thread has put a new node there. So if some thread is doing work, that's okay, it's lock-free. Now, wait-free goes a step beyond that and gives you the guarantee that all threads are always making some kind of progress. And in fact, they're going to finish that call, that execution, in a finite number of steps. Now, so far, no academic has proved that wait-free always gives better performance than lock-free. And in fact, under no contention, so just a single threaded, it seems that the other way around is true, is that lock-free provides better performance, throughput, let's say, better throughput than wait-free, but not under high contention for sure. So a thread with wait-free calling a method that's wait-free will always make progress if the thread scheduler gives it CPU time, of course, otherwise no progress will be made, and it will never starve. So there's no starvation, unlike on lock-free. So one thing when you think about wait-free that's not obvious is that wait-free is not free from waiting. Like I said at the beginning, there's no time associated with this. So even wait-free methods still depend on how much slices get from the thread scheduler, how much time the thread scheduler gives it to execute. If you're running on a low priority thread and you keep getting preempted by higher priority threads, it doesn't matter that you're running a wait-free method, you're never going to run, so it's never going to complete. So you cannot translate the wait-free progress condition directly into time unless you have some kind of guarantee from the thread scheduler that you're using. So that's from the task manager, whatever you want to call it. So wait-free and time is not immediately the same thing. And then you have the best kind of wait-free, which is population oblivious, which means it's a finite number of steps and it does not depend on the number of threads. Examples of this can be given with atomics. For example, doing a simple load is always wait-free, and a simple star is also always wait-free, population oblivious. Doing an exchange or fetch and add, is Wait-Free Population Oblivious on x86 because it's a single atomic instruction. It's exchange, and the other is x-add or lock-add. And compare and exchange strong is also, assuming you're not running it in a loop, of course. If you're running in a loop, then it will be lock-free. On other architectures, it depends. You'd have to check. So, another thing that people usually say is that, oh, this data structure is lock-free. Well, if you say that the data structure is lock-free, then you're implying that all the methods in that data structure must be at least lock-free. Because the progress condition is something that you associate with the method, not with the whole class. Even though you need the whole object, the whole thing, but you characterize it for a method. So in this case, I artificially created some class called cookie, and you have 3 methods. Now I would like you to think about what are the progress conditions of each one of these methods. Let's start with the easier one, get cookie type, which is doing an atomic load on the variable type. Which of these do you bet on? D, Wait-Free Population Oblivious. Any other bets? D, okay. So in fact, it is Wait-Free or Population Oblivious because atomic loads are always Wait-Free. Population Oblivious. Oops, sorry, I already showed the answer. You didn't see it. So then you get total chocolate chips. And what it's doing is it's going over an array of atomic integers, and it's reading each of them. And now the thing about this array is that it has the size of the maximum number of threads in your application. So it depends on the number of threads. So what is the progress condition of this method? Wait-free bounding. That's right. Because it's bounded by the number of threads. If you increase the number of threads, you're going to have to do more work. So it's a higher number of steps to complete. And then you have add chocolate chips, which is doing a load over there on the chocolate chips, the first entry in this array, and then just incrementing by 1 using a compare and exchange. Yes, that is correct. Okay, now let's take a very short look and very light thing on how progress conditions affect distributions of latency. This is just how the tests were done, but it's really not interesting. So suppose you have a lock, and you do some work inside this lock, and now this work usually takes something like 3 or 4 microseconds to complete, and then you release the lock. Or at least the whole package, like acquiring the lock, doing the work, and releasing the lock, takes about this when you're running in single-threaded. Now, the thing is, if you start adding more threads to do the same thing, obviously the lock is going to serialize this, so they're going to take twice as much because they're going to have to wait for each other. Only one of them at a time can do, so that means you increase the latency, so the average time it takes. And if you add more, it starts to go 3-4 times. So it's more or less linear if it works okay, if the lock is not too bad. But as you can see, it's not just linear. There are some other things going on here, and the problem is sometimes a thread doesn't get it, let's say, on its turn. It's not a round robin because this is a spin lock, for example. It's not necessarily fair. So it doesn't get it on this turn, so it's trying to get it on the next term, or the next one, or the next one, and you can get, you can have a really big wait. You have to, so maybe I didn't explain this plot very well, but on the x-axis we have time, so how long it takes for a certain task to complete, and on the vertical axis we have normalized histogram. So I used to be a physicist, so we like histograms a lot. So that's how it does. So if you have more threads, you keep on getting more distributed peaks. And in fact, these peaks are going all the way up to infinity, or, well, not infinity because the tests, so I only ran the test for 30 seconds, so that would be 30 seconds or something. But you get a fat tail in the distribution. That's usually how statisticians call this kind of stuff. And as you can see, when you go to 16 threads, this is on a machine with 18 cores, so we're still under the number of cores that we can put. You know, okay, so there's like less than 10% are around here or something, but most of them take a really long time to complete because, you know, there's starvation, they're going on. So if you put all of this, you see that, you know, there's a fat tail on this distribution, which means it's not good for latency. You want latency that's the more to the left as possible. Now, if you use a starvation-free lock, you still see the same kind of behavior where as you add threads, you have to wait more, but there's no such thing as these extra peaks, this extra delay. Now with 8 threads, you get some convolution that makes it smear, but, and this one you don't see it because it's after the 50 microseconds, but I've shortened this one and you can see it's the orange hill there. So you don't see the fat tail here, you just see the delay because now you know that it's going to have to wait for n-1 threads. So if it takes 3 microseconds for one thread to complete, you're going to have to wait n-1 times 3. So all of the threads on average are going to wait for that. So you get a peak on n-1 times 3 or 4, whatever it is. So how about lock-free? Everybody talks about lock-free. Lock-free is great. Yeah, great. Lock-free. Yeah. Well, when you start adding lock-free, I don't know if you're seeing, but there are some little peaks there. Yeah, because lock-free is starvable. You can starve with lock-free. So what you're going to get is, again, the same kind of behavior, but this time you're not sliding because it's lock-free, so you can get stuff done. But the tail can go on again for up to infinity, although infinity doesn't actually exist. It's just a mathematical construct. But that's another story. And then you've got wait-free, or wait-free, sorry, is that bounded? Yes, bounded by the number of threads. In this case, all of them are doing work, so because it's bounded by the number of threads, the more threads you add, the more work you're going to have to do. So again, it takes longer. In this case, it's linear with the number of threads. You can have O1, that would be, well, not O1, but O log n, that would be great. But sometimes you can get O(n) squared, and that would grow with that order. So you see the advance, but you don't see the long tail. Wait-free doesn't have this tail. And of course, the best of all, Wait-Free Population Oblivious, which shouldn't even slide to the right or anything. And this time it went back, which is weird. But anyway, it's always more or less on the same place because it's not supposed to take longer just because there are more threads. And there are no tails as well. So that's a really good latency distribution. If you go look at the 99.999%, there's nothing, right? There are no events there. All of them are, the 99.9% is very close to the median, let's say. So what this matter, as a kind of summary of that, blocking and lock-free have a fat tail on the latency distribution, wait-free, and starvation-free sometimes. Depends on how many cores you have in threads and other stuff. But those generally don't have a fat tail. So this is just, again, the same thing. Wait-free methods have what you can call a cutoff, a maximum latency, beyond which you know that you won't have to wait more than that. That's a very powerful guarantee. It's extremely powerful and extremely important in low latency scenarios, of course. Okay, so apart from that, maybe something I didn't mention is that memory allocation and deletion is usually blocking. So if you have an algorithm that is wait-free, but it's allocating or deleting memory, well, do you really call it wait-free? Because it might do something that is blocking. It's a bit of a gray area. And the most desirable kind of blocking, I would say, is starvation-free because of its latency guarantees, and the most desirable of all progress conditions is wait-free population oblivious. Okay, we're a bit behind, so I'll save questions for later. So how about, now that we talked about progress conditions, let's start to go into the cool stuff. So reader-writer locks are a way to protect your data. And at the same time, they allow for multiple read-only operations to be ongoing. So this is really cool for data structures where you're doing read mostly. And recently there has been some, so in C you got pthread, reader-writer lock, Boost as shared mutex, C++ 17 as shared mutex, and 14 as shared time mutex. There are many different kinds of locks, reader-writer locks, we won't go into that. There are some really cool new algorithms like the cohort reader-writer lock write preference, which scales extremely well for readers as long as you're doing mostly read. And this is very recent. And it's a paper by the Oracle guys, and we have some implementations of that because we came up with almost the same idea at the same time. Now, if you want to protect a data structure or whatever you want to protect with a reader-write lock, you know, if it's a pthread, it would be like this. I didn't have time to put the new one, the new shared mutex thing. It would be even easier and prettier than this. But basically, you just protect. If it's read-only operation, you protect with a with a read lock. If it's a modification like an insertion or a removal, then you protect with a write lock. That's it. Really simple. So that is one way to make a concurrent data structure, even though it's completely blocking, but it's concurrent. You can access it safely from multiple threads. But there are other ways. One other way is copy on write. Now, most people, I think, call it read copy update, maybe. I'm not sure. What it is you have a data structure and you have an atomic pointer that's pointing to this data structure. And whenever you want to modify the data structure, you don't. You just make an entire new copy of it in private. You modify whatever you need to modify, and then you toggle the pointer. That's it. And now you have to take care of safely removing this memory, and that's the hard part. Usually it's done with RCU, but you can use other pointers as well, other stuff. This scales really well for reads, as long as you're doing only reads. But as soon as you start doing a little bit of writes, well, you have to copy an entire data structure, and that's really wasteful and slow, extremely slow, of course. And then you have to call RCU synchronize and stuff like that. It's gonna take ages. So how does this work, more or less? Well, you've got a thread that wants to do modification, so it does a copy and calls it instance2, and then atomically changes the reference. This is an atomic reference, let's say. Well, not a reference, whatever. And then the new readers can go read the modification, and the write, and another thread wants to do a write, goes and makes another copy. So there are multiple instances. You could theoretically have multiple instances. When you use RCU, actually you can only have 2 instances at a time, but it depends on how you decide to manage your memory. And the thing about this is that it has a property called linearizability, which we'll go into more detail if we have time. And it's the same kind of property as a mutual exclusion lock or a reader-writer lock. So it provides the same kind of stuff. So this is the good part, left-right. So this is a technique that Andrea and I discovered some years ago. The cool thing about this is that it can safely be used in C++ because it has its own memory reclamation. It has some nice properties, one of them being linearizable, which is what everybody likes. And the idea is kind of like a double buffering technique in computer graphics, if you're familiar with that. It's like on computer graphics you have 2 drawings, 2 buffers going on, and you're drawing in one while the other one is being shown. Then you swap them. Well, this is kind of the same thing. You have two instances of a data structure. You're modifying one, while the other one is being accessed by the readers, and then you toggle them, and the readers go on the other one, and you modify this one after a while. So that's kind of the idea. Now, if you want to actually implement the algorithm, it's simple. I'm going to talk a little bit about that, but you don't need to know how to implement. You can just use it if you want to. Just copy-paste the code, and using that, we'll see as well how to use it. It's really simple. So basically, these are the components of the algorithm. There's a mutex. There are two read indicators, which are like counters, and two atomic variables, a version index and a left-right, and then two instances of whatever you're trying to protect. Typically, it would be a data structure, but it can be anything you want to protect. So let's see. Suppose you want to protect a stud map. So the first step is making two stud maps, and you place them there. I've represented them as being these little guys here. And now suppose you want to modify. Well, what you do is you grab the mutex, and then you go on the left, right, and you see, oh, it's pointing to this side here, right? So that means all the readers are coming here because the readers look at this variable. So I'm going to modify immediately that other data structure. Once the data structure is modified, which is in this example, where is the pointer? We inserted the element 9. Now we want to do the same thing so that we have mirror of each other. So the writer comes back here, has to wait for the read indicator to go to 0 or go empty, toggle that, then again, and then can go and safely modify and release the lock. So what it does, it's really simple. On the reader side, they don't acquire any lock. They just go in, look at the version index, that's an atomic load. They do arrive on that, which is usually just an atomic store or a fetch net. Then they go on left, right, and see which data structure should I go into, and they do whatever read-only operation they need to do. And at the end, they go and do the part, which is, again, an atomic store or an atomic fetch net. So this is the first part of the mechanism. It's called arrive the part and toggle version and wait. But actually, if you know RCU, that Bob McKinney was talking about yesterday, this is actually a kind of implementation of that. So you can replace it with RCU if you want to. That would work. Okay, I forgot about that. Now, you could, the way to do that, the way to actually use that, well, not to use, but how to implement with lambdas would be with something like this. I'm sure there's a better way to do that, but I didn't have time to research that. So the actual algorithm is the readers, when they want to apply a read-only operation, they do arrive, which is kind of like RCU read lock, let's say. Then they look at the variable left, right, and they apply the they apply the read-only operation based on whatever the left, right was, and they do the part, which is like RCU read and lock. And that's it, that's the only thing they do. As for doing a mutation, so in this case it would be like an insertion in the stud map or a removal on the stud map, then the first thing you need to do is acquire a mutex called the writer's mutex, and then you look at the left-right variable and you go and modify the opposite one because the readers are on the one that left-right is pointing to. So you go and modify, apply the mutation there, then call this thing, which is kind of like an RCU synchronize. Okay, so that's how you would implement the background, but how would you actually use it? Well, again, I'm pretty sure there are many easier ways to do this, but basically you just need to pass a lambda that's doing whatever you want to the data structure that you chose. So in this case, it's a stud map that maps integers to some user data class. So you just, if you want to do a find that's concurrent, you just pass map find of the key. In this case, I just want the Boolean. I don't care about the rest. And if you want to do a removal, you just call map arrays inside, and insertion is insert. And then you have to pass this depending on whether or not it's a read-only operation. You do apply read or you do apply mutation. Now, there are a lot of variants of this algorithm. There are a lot of variants, and this one is the one that I like most. It's the classical one because we can choose the read indicator that we want. 45, okay. So what is the read indicator? I've been talking about that, but I didn't explain. So basically, for the purpose of this talk, read indicators have three methods. That's arrive, depart, and is empty. And they have to be sequentially consistent or at least linearizable. And the simplest of them is just an atomic counter where you do fetch and add on the arrive, fetch and add -1 on the depart, and to see if it's empty or not, you just do a load. So basically, this is what the readers are going to call when they want to enter a critical section. They will be doing arrive. When they leave, they call depart. And when the writer wants to know whether there are any readers or not, it's going to call is empty. But there are, on the left, right, there are two read indicators. So you can get it a little bit more complex, but more scalable, because the problem with, let me go back. The problem with this one is that, well, if you have 10 cores and 10 readers hammering the counter variable, all of them doing fetch and add, it's going to kill your scalability. You don't want that, right? So how do you do something that's scalable? And by the way, this one is Wait-Free Population Oblivious for all operations, on x86 at least. So the trick here is to create an array of counters, and you put cache line padding on each entry. And then you can either assign an entry to each thread, but that's hard to do in practice. An easier way is just to get the thread ID and hash it and distribute it randomly in one of these entries. And you need the cache line padding because you don't want false sharing. But once you get that, statistically, you have very little contention. You can even increase the size of the array to as much as you want, right? As much as you're willing to spend in memory. But usually a few times the number of cores, that's enough to get good scalability. And then you can optimize reading the array, because of course you could do all of them sequentially consistent loads, but instead you can do some tricks and do just one sequentially consistent load, and then read all the other entries as relaxed, and in the end you do some atomic thread fences so that there's no reordering. So in this case, atomic thread fence is preventing all the relaxed loads from going below the fence and anything from going above the fence. So that's a nice trick, and it gives you good performance. But like I said before, if you know how many threads you have in your application and you can assign an entry in the array for each of them, then okay, even better. Then they don't have to compete, and they can just do a regular store saying whether there's a reader there or not. So that's even better. I'll skip that. Okay, so how do we know if it's correct and how it works? So this is the state machine for the writer and the reader. It may look complex, but it's not compared to most synchronization mechanisms. This is really simple, actually. Now, the thing about the reader state machine is, in this case, for example, you're doing a transition. If the version index is 0, you transition from A to B, but if it's 1, you transition from A to C. So, okay. But the interesting part about this state machine is that there are no loops in the state machine. It's always going forward, let's say. There's no way to come back in the state. On the other hand, for the writer, there are loops because they have to wait for something to happen, in this case for while it's empty. So now I've put the whole code back in again, and And quiz 4, what is the progress condition for mutative operations on left-right? Now, I'm going to try to help as much as I can before anybody says something. So the first thing you notice is there's a lock here. You get a stud mutex, and you're locking writer's mutex. And then there's an atomic load there, and then here there's this method call, which is doing some loops yielding. So anybody wants to guess which of these it is? Yes. Well, it is starvation-free if you use a mutex that is starvation-free. I don't think the default one on C++ is starvation-free, but if you use one that is starvation-free, then everything else can be starvation-free. So I think that's the right answer in this case. Very good, you're paying attention, that's nice. And now the same question, but for the readers. Now the readers, what they do is they call arrive and depart, which you see here. And you can think of this one as being a fetch and add, and that one as being also a fetch and add. And then they do an atomic load. So basically what they do is fetch and add, atomic load, fetch and add. What progress condition is that? Population oblivious. Yes, that is correct. Now you could think that it is population oblivious immediately from the state machine because the state machine has no loops, so that's, well, wait-free. At least it would be wait-free for not having any loops. And the thing about the writer is, yes, it is starvation-free because the writer only has to wait for older readers. Even if new readers come in, they are going to go on the other instance, and the writer doesn't have to wait for those. He just has to wait for the old readers. This is the typical RCU thing. Okay, so how about consistency? Now, there are a lot of different types of consistency. There was some talk yesterday about that. Linearizable is one of them. Sequential consistency is another. There's serializability. There are loads of relaxed stuff. And there's even strict consistency, which is impossible for data structures, at least on this kind of hardware. So the thing about concurrent data structures is that if they're not at least sequentially consistent, it's very hard for the human brain to understand how they work and what kind of behavior to expect out of them. Yes, you can make something that's more relaxed and sequentially consistent, something that's, it's going to give some weird values, but you really don't know what to expect out of it. So even if you give it, you have this really pretty concurrent data structure, ultra fast, and you give it to a software developer, and he might not even know what sequentially consistent is, but he has some kind of expectation on how it should behave in terms of how consistent it is. I mean, what kind of results it should give in certain situations. And the thing that he has in his mind is usually called sequentially consistent. Well, at least that's how it should work. So linearizable is almost the same thing as sequentially consistent, but slightly stronger. It means that you can find at least one instance in time where the operation appears to become instantly effective. Now, and this is the property that mutexes have. That's how this is what mutexes give, the kind of consistency they give, and reader-writer locks. So let's say left-right, in this particular case, the left-right variable is pointing there. You get the readers going there, but as soon as the writer toggles the left-right, then the new readers are going to see the modification that the writer is doing. So this is what is called the linearization point. From this moment on, when that atomic variable called left-right is toggled, that means that the modification is now visible to new readers. So that's the linearization point from writers to readers. Is there anything? And okay, so maybe just stating the obvious here. These two data structures, they don't have any atomics inside. Those are plain single-threaded data structures, just like you would put on a reader-writer lock. There's no atomics here. You don't have to do lock-free or wait-free programming to get this working. More about linearizability. So one of the advantages of the left-right and similar techniques, well, in this case, copy on write, and reader-writer locks also give this, but not with wait-free progress, of course, is that you can do linearizable iterations, linearizable read-only iterations. Well, and mutative as well, but those are blocking. So there are a lot of lock-free data structures, well, some lock-free data structures out in the wild. We talked about one like Michael and Scott queue or list, where it's just a linked list where you add nodes in the end. And the thing about these data structures is that if you want to do a read-only iteration, for example, to count how many nodes there are in the linked list, the result that's coming out of that is not linearizable. It's not linearizable for sure. So what does that really mean? Let's see some example. So suppose we have one thread that's just reading, and it's going over a linked list that at this moment only has 3 nodes. That's all that there is. And now there are 2 threads here. The animation is not complete, but one of them is going to add new nodes at the end, keeps on adding, and the other one is like removing the back ones. So it's like, oh, the reader is counting 1, 2, 3, and then the other thread comes in and puts a new one, and the reader is like 4, 5, 6, whatever. It's going on forever. Now notice that there is no moment in time where there are more than 3 nodes in this data structure, in this linked list. There are never more than 3. It's either 2 or 3. There was no other moment in time like that. And what is the reader going to say in the end? Well, it's going to say that the size of this list is 11. Like, really? That's how lock-free linked lists work nowadays. Okay. So, that's not surprising to anyone. Okay, that's fine. So it's like 11? How is this possible? What's going on? It's like, so what this means is that the method that counts the number of nodes in the linked list is not linearizable. But if you do this with left-right, you're going to get the answer 2 or 3, depending exactly on what's going on. There's no 11 coming your way. The same thing if you use a reader-writer lock, but then it will be blocking the answer. But left-right is going to give you a wait-free population oblivious answer. That's the advantage. So let's compare against a reader-writer lock and against a copy-on-write technique. Remember, the copy-on-write is the one where you have to make an entire new data structure whenever you have to make one single modification to it. It's like, so we have on the top 4 plots a stud map with 100 items in it, and on the bottom 4 plots we have a stud map with 1,000 items. And this is x86 with 18 cores, that's 36 hyperthreads. I don't think you can read the legend, but the blue one is reader-writer lock, pthread reader-writer lock. The red one is left-right with atomic counters. And the green one is left-right with an array of counters, cache line, added to the cache lines, and then hashed on the thread ID. And the copy-on-write is the purple one, magenta, plus RCU to save the memory. So as you can see here, they're pretty much all the same if you're doing just writes. If you're just doing modification, it's kind of like doing a reader-writer lock, except, well, the reader-writer lock is slightly better for one thread, or I think, yeah. But as soon as you start doing more reads, then it starts to get really better. And if you're doing only reads, then it's nearly linear scalability. That's really something hard to get. Same thing for 1,000 items. One thread, the reader-writer lock still wins, but everything else, and over there with some oversubscription, I guess. But as soon as you start doing more reads, well, then the left-right technique is going to get better, and for only reads, you get, again, linear scalability. That was on x86. This is on PowerPC. The results are more or less the same, so I'm going to skip that. Now, the interesting part is latency. Now, this table is a bit confusing, but you can read it. For example, if you look at the first entry, what this means is on a reader-writer, when using a reader-writer lock, 99% of the calls to find finish in 51 microseconds or less. So this is like the latency with a certain precision or with a certain, how do you say, quantile, not a quantile, but. So the lowest this is, the better. On reader-writer lock, yeah, you go 70, 40, whatever, as you start having more. And on left-right, it's always 2, 3, 7, it's like an order of magnitude below. So that's really impressive. Now, the copy on write can also do the same, even though you can't really see it there. But when you do modifications, well, when you do a modification, you have to copy the entire data structure. And copying the entire data structure means it's going to take forever. It's like, forget about latency. Everything's so slow, whatever. And now another thing. Okay. Okay, so one thing that you might think of is, well, you have two data structures and you have to do the same operation on both. Isn't that like kind of slow? Yes, if it's a long operation, but think of a stud map. You protect it with a reader-writer lock, for example. The time it takes to acquire the lock can be so slow that the time it takes to do the modification is kind of negligible compared to that. So in many cases, you can say like the mutation just takes this long, but the actual lock takes much longer. So doing twice the mutation, well, you're not going to get it such a big slowdown as you might expect. And in fact, when you do one over the other, a ratio, it's very close to 1. Sometimes it's even better. Well, there are fluctuations, but it's also because we're using stud mutex, and reader-writer lock might not be as efficient as that. P-thread reader-writer lock. Yes. So, this is a harder one. Now, another thing that is non-obvious is when you have a lock-free data structure, doing any kind of operation requires traversing some kind of node or traversing the data structure somehow. And usually to do that, you have to do, at the very least, acquire loads whenever you go through another node or doing something. Now, on x86, you can see here that doing an acquire load or doing a relax load, it's the same thing. It's just a move from memory. There's really no difference. So there's no impact on performance. But other architectures like PowerPC and ARM, well, that can be a pretty big difference because this one is doing async and that one is not doing anything. So when you use a left-right technique to go through a really large data structure and you're going, through all those nodes, well, it's kind of like doing a relaxed load because it's just they're just regular variables. So you're not doing any memory fence behind, so it's much faster to do any traversal. So that's an advantage, usually. For example, if you think about, for example, Michael and Scott list, which is the one we saw before, on PowerPC, it's going to do n times an async barrier, where n times is the number of nodes that are being traversed. While if you look at a list with left-right, it's going to do 3 HW syncs because it's related to the variables left-right and version index. So one is a fixed number, the other one is n. So which one is going to win? I think that's more or less obvious. So the blue one is the left-right, and these two are the other lists. One with sequentially consistent atomics, and the other with sequentially consistent loads, and the other with acquire loads. Now on x86, the difference isn't that big. In fact, the blue one, which is left-right, loses a bit because it has the overhead of calling, 5 minutes ago. But if you take into account that the other techniques need some kind of memory reclamation, like hazard pointers, and if you have to inject hazard pointers, that means every node that you go through must have a store for the hazard pointer, then the performance completely drops off, and left-right doesn't need that. It does its own memory reclamation safely because it has like an embedded RCU thingy. So you get better performance. Yes. So if suppose you don't like this and you want to do, you think this is still too slow, you have to do the same work twice. Well, for a linked list, there's an alternative. And the alternative is the following. Now, suppose you're just using left-right as usual, and that means you have on a linked list, so there's actually two linked lists, they're pointing to the same keys, right? There's the left instance where it has that and pointing to that key, and the right instance pointing to that one. But in fact, you can combine the two lists and and have one node for each, and the readers are either traversing on the next left, next left, next left, or they're traversing on the next right, next right, next right, and they're not going to touch the other one. So you can apply the same principles as left, right, but you can't do this with Lambda. You have to manually hard-code this. And it's safe to use, and it's just one linked list, and you just have to do the work kind of once. Suppose, for example, in this case, you want to remove one node. Well then, you would go over here, unlink this one, wait for the readers to toggle to the new one, so that they would see the modification below. Then you do the other modification, and then you could safely remove the node. So this way, you don't have to start from the beginning of the linked list, search for the node, and then remove that, and go back to the beginning, wait for the readers, and then find the node. Because it's the same node, so you just go over to the node, remove it, wait for the readers, and then unlink the other part. So unlink one part, unlink the other. So you don't do the same job twice, just once. And obviously, this is much faster. It's still blocking for insertions and removals, but it's wait-free for readers. Why is that twice? You already saw that. You'll get bored. Okay, so some people see that and they think left-right is like RCU. No, it's not like RCU. RCU doesn't even have two instances. But there are parts of left-right that can be replaced with RCU. Like I said before, arrive can be RCU read lock, depart read and lock, and toggle version synchronize RCU. And this is the last slide, kind of. So suppose you have all the RCU algorithms and you can get any of them, and you can use the copy and write technique that we talked about that makes an entire new data structure every time. Well then, you can get a single data structure, apply that technique, and what you get in the end is a concurrent data structure, safe to use, memory-wise. So that is wait-free for reads and blocking for mutations, but that's fine. It's safe memory-wise. The memory reclamation is done for you in the data structure. That's very precious. And of course, you can do the same thing, RCU plus a concurrent data structure like Harris linked list or Michael and Scott linked list. And in the end, you get a memory reclamation concurrent data structure. Now, you can also get any of the left-right algorithms. You combine it with two copies of the same single-threaded data structure, whatever single data structure you want, and again, you get the same result. You get a data structure that's safe to use in a concurrent setting for memory. In fact, you can interchange any of these with any of these solutions, and you get a concurrent data structure safe to use with memory reclamation. So that's extremely powerful. That doesn't matter, I'm going to skip that. So the last takeaways I want you to take from this is you get linear reusability, mutual exclusion for any object or data structure with left-right. It's interchangeable with RCU, kind of, the things that you do there. And you get almost linear scalability if you're doing mostly reads. And you can just copy-paste the code, kind of put it in your application, and that's it, and use some nice lambdas. And it's Wait-Free Population Oblivious, which is like the best kind of wait-free there is. So that's it. So one thing I forgot to mention is, even though this presentation, if there are any rare errors, they're my own, but this is based on work that I've done with Andrea Correa, and we have a website called Concurrency Freaks. We put a small part of the work we do, we put it there, if you want to check it out. Yes, I think there's a microphone. Yeah, you can, I think the microphone is on, if you want to ask, so that people at home can hear the question.
Right, hi. So this is not a question, but just a comment regarding visualization. So when you show this table with percentiles of your latency, there is a nice way to visualize this. I think it's from the finance guys. There is this exchange called LMAX. And what they did is to have a high density range histogram. So you can go to GitHub and basically look for HDI histogram. And it basically visualizes the latency of trading operation across the percentiles. So this way, just from the profile of this latency histogram shape, you can actually find very interesting patterns in your trading execution guarantees. So that might be something you may find also interesting.
Thank you. Yeah.
So any other question?
Yeah, in the array-based counter implementation where you have like thread-indexed array for reader counter, I mean, you're going to basically harvest the entire array in the writer. How do you know that after you went for elements 0, 1, 2, 3, 4, some reader doesn't bump up element 0 again?
So that's the thing about sequential consistency and the algorithm itself. So let me just check that. I think I know what you're saying. Yeah, that's the one. So the thing is, you're only going to call the, maybe that's not the right one to show. Okay. See, the thing is, you're only going to call a version index to change which of the counters, so which of the read indicators is going to be changed, is going to be arrived departed by the readers, and only then you call is empty. So if there's one thread that's going to, one reader thread that's going to, it can still increment, like you said, it can increment the first entry of the array. That's fine, because there is no direct matching from the read indicators to which instance is going to be used. What happens is you get an happens before relationship, which is if the reader saw the new version index, then for sure it must see the left-right variable changing. That's all you need. So what can happen is you can get like false positives where the writer is waiting for a reader that's actually already on the new instance, but it marked the opposite read indicator, just like you said. It can happen. In practice, it's extremely rare because this is like, happens just for a little while. But that's the reason why we need to wait twice. One for the opposite read indicator, and then again here for the other read indicator. So this wait here is to prevent the case that you just said. That's related to the algorithm of the left-right itself.
Okay. A minor note, when you were doing the ticket lock, you go through overflows there. They should be unsigned loans, pedantically speaking.
Yes, that is a very good point. Yeah. Thanks.
So any other questions?
There's one more.
Just wondering, how do you deal with failures to insert in the second copy of the collection? Do you fail fast? Do you undo the first one? So let's say you inserted successfully in the first three, but then fail to insert to the second one. What do you do?
They are mirror images of each other, so there's no reason for them to fail.
Well, let's say if allocation is involved, if it's map, std map,
yes,
then allocation might be involved out of memory.
Then you return failure, and
pretty much
if you have a problem like that, it's
fail fast. There is no undo in your case, right? Because I could, well, you're saying your strategy is fail fast in this case.
Yes. If you have that kind of problem, you have other things to worry about, right? It's like you ran out of memory, yeah.
Thank you.
There's another one there.
One of your slides you mentioned read-write, that there were some advancement made in the reader-writer lock. Could you tell us something more about that and whether that changes any of your results? Because you compared with the...
Yeah, I don't have here the comparison I did with that. I think I did it some really long time ago. It's this one, the NUMA-aware reader-writer locks. I didn't compare with that, but the latency isn't as good as left-right, obviously, because it's a reader-writer lock. It's still blocking for readers. So you're not going to get the same latency out of a reader-writer lock, no matter how good it is, which is actually pretty good, that reader-writer lock. But you're not going to get the same kind of latency out of it. And even throughput, in the end, depending on the exact workload that you put, whether you put more readers, more writers, even the throughput is not as good. It's not as good. But I don't have plots to show you with that, sorry. Maybe next time.
All right, thank you. We are way over time. Thank you.
Thanks.